Next, I would like to invite Dr. Ahsan from Anhui province, China. Dr. Ahsan,
Hello, can I audible to you?
yes, yes. Please share
Okay,
your screen.
okay. Good evening, everyone. Assalamu alaikum. Let me begin by expressing my sincere gratitude to the organizing committee of ICCRT for putting together this wonderful forum on current research trends. Special thanks to Mr. Osama Afzal and his entire team for their tremendous efforts in making this event possible. I'm truly honored by invitation to speak with you all today. Let me share my screen. Uh, is it visible to you?
Yes, yes,
Can you confirm the transition changing of slides?
yes, please.
Okay. Thank you. So I have done my PhD in electrical engineering from Tianjin University, China. Nowadays, I'm working as a postdoctoral researcher with the School of Electrical Engineering, Tongji University, China. The topic of my presentation is evolution of machine learning models for renewable energy forecasting. Uh, it's not moving. Why? Is it seeing to you?
Yes, please continue.
Here's the content of our presentation, which I will discuss one by one. So, as you know, all that the world is experiencing an increase in energy demand due to its population growth, and presently this energy demand is relied mostly on fossil fuels. But by the end of 2050, it will shift from fossil fuels to renewable energy. And in the renewable energy is basically eco-friendly nature derived directly from nature resources. We have different type of renewable energy: solar, wind, biomass, geothermal, and others. And solar is a basically wide range of renewable energy is very crucial. And in next 30 years, we can generate around 8,300 terawatt of energy per year by this solar energy, and then wind, and then others. So basically, this solar energy is directly come from sunlight through PV cells. And despite advantages, there are other disadvantages of this variation because of geographical location, weather locations, and system size. So fluctuation in solar radiation can mismatch between the solar generation and the customer demand. And by using AI-based machine learning models, we can improve this energy system more effectively, adaptively, and we can use it sustainable energy resources. So accurate forecasting is very important in renewable energy, like parameters like power generation, grid connection, and solar radiation. So accurate forecasting also very effective in management of grid operation, adding power planners in optimizing distribution, and it's also has served as a fundamental tool for decision maker in energy sector, which make it forecasting more resilient and responsive power infrastructure. So the problem and scope of my research was basically unpredictability, uncertainty in renewable energy due to weather and other conditions. There are uncertainty in solar power generation or renewable power generation, which can affect the grid stability. It will affect grid reliability, and it also creates challenges in integrating renewable energy into grid. Due to by accurate forecasting, we can utilize and optimize and use the efficiency and of this power plant, and schedule a maintenance for improved performance. It will directly impact the revenue because what we generate and what we sold to the customers and supplied to the grid. So it is directly related to revenue. Also, it has environmental and economical benefits it's directly related to United Nations SDGs 7 and 13. So there's the research objective of my presentation. It's the diagram shows the flow chart using different model for power generation for forecasting. We start from the importing the data set using solar power plant. Then we use different techniques like pre-processing to validate the data. If the data is validated, then we can go further. If data is not validated, then we have to again pre-processing some to decrease to minimize the outliners and something other errors in the data. Once the data is okay, then we will implement the model. And in my research, I have implemented several models. I started from Ariva model, which is a statistical model used for forecasting. Then I moved toward machine learning model, which is SVM, RF, random forest. And finally, I found that the deep learning model, which is RNN, GRU, LSTM results were among the best using these all model. And LSTM results, long short-term memory result was among the best using deep learning model, machine learning models, RIMA models. So I further improved this LSTM model using autoencoder LSTM model and further enhance this two different hybrid machine learning, deep learning models by combining CNN autoencoder LSTM model and ANN autoencoder LSTM model. So I finally found that the hybrid autoencoder LSTM model results were among the best in comparison of all these previous models. Once model is implemented, we will split data into training and testing. And after model implementation, we will test the model. And once testing is done, then we will predict and visualize the results. Here's the solar power plant parameters which I have used for next year generation. These are daily power generation which we measure in kilowatt hour. Then we have maximum grid connecting power generation, which is basically grid efficiency with megawatt. And third one is solar radiance, which the solar radiance is it's measured in megajoule per meter square. So there's the performance matrices from where we can calculate our which model is doing best and we have which have the lower results. So these are ME, MSE, map error, and root mean square error. So here's the results, error results of implementing all our models starting from ARIMA. Then we move toward SPM, RF, then deep learning model, RNN, GRU, LSTM, then autoencoder model, and then further finally hybrid ANN, CNN, ANN autoencoder model, and hybrid CNN autoencoder LSTM model. And you can see from the results that ARIMA have the highest MAE, MSE, even MAP and RMSE error in terms of all the parameter, daily power generation, grid connecting power generation, and radiance. As we move further to other models, the hybrid CNN autoencoder LSTM model have the lower MAE, MSE, MAP, or MSE, all matrices results in cross all the parameters. So figure number 6, 7, 8 shows the mean absolute error for daily power generation, grid connecting for power generation, and radiance. And you can see from figure number 6 that starting from RNN, which is deep learning model, have high MEE values. But as we move toward further, the CNN autoencoder LSTM has the lower MEE values. Same as case for the grid connecting power generation, hybrid CNN autoencoder LSTM have the lower ME value across 100 epoch. 100 epoch we are taking when we are doing training and testing in machine learning. And similarly, if radiance in radius case, parameter case, CNN autoencoder LSTM has the lower ME values. This in this slide we have a mean square error starting from RNN, GRU, LSTM across 100 epochs. The figure number 9 shows the MSE for daily power generation, and you can see that the CNN autoencoder LSTM have the lower MSE values. Similarly, figure number 10 shows the MSE for grid connecting power generation, and in same case, hardware CNN autoencoder LSTM have the lower MSE error. And figure number 11 has the MSC for radians, and similarly, the hybrid CNN and encoder LSTM have the lower MSC values for radians parameters also. So here's the power generation predictions, which we have started from our deep learning model, and then we toward the hybrid models. From the figure, first figure, you will see that the blue lines are very out of ranges, and they are very distant from the test data. In the other case, the CNN autoencoder LSTM prediction, which is in the red line, is very much similar to the test data, and very much and we can also see from the previous results that from the previous error result that the CNN autoencoder LSTM have the better predictions in terms of daily power generation across all the other models. Similarly, results were found in grid connecting power generation prediction. The hybrid CNN autoencoder LSTM results were among the best in contrast to ANN autoencoder LSTM, simple LSTM prediction, GRU prediction, and RNN prediction. The CNN autoencoder LSTM has a very low distance to the test model data, and its prediction are very good as we seen from the error results of MAE, MSC, or MSC map error. And in this slide, our third parameter, which is solar radiance parameter, the RNN result were very different from the test data. Similarly, GRU has some better result, but finally the LSTM has the better result than GRU or RNN. We further improved this LSTM by using ANN autoencoder LSTM, CNN autoencoder LSTM, which is a hybrid models, and we found that the hybrid CNN autoencoder LSTM has the better prediction results in terms of radiance parameter across this full year. So what we concluded that accurate forecasting of solar power generation is very essential in grid stability, and it basically unpredictability of renewable energy helps to balance the grid operation and lower operational costs. In this research, we started from ARIMA model, which is traditional statistical model used for machine learning, used for forecasting, and then we moved to the machine learning models we are using SVM, RF, and then we further improve our forecasting using a deep learning model RNN, GRU, LSTM, and then I found that the LSTM result were among the best using GRU, RNN, RF, SVM, and RIMA. I further improved this LSTM using autoencoder LSTM, and further enhance this by implementing hybrid model, which is a combination of ANN autoencoder LSTM and CNN autoencoder LSTM, and CNN autoencoder LSTM outperformed all the other previous models in terms of different matrices like ME, MSC, MAP, RMSC, and gave us a better prediction, which have very little distractions in comparison of the test data. We have used real-time solar power data to implement this, and for further accuracy. And yes, accurate renewable energy is basically improved maintenance. It's basically direct relate with the revenue and profitable for energy traders. And by improving this forecasting, we will support renewable energy in sustainability, environment and sustainability, and it will reduce greenhouse effects. So what about future work? We can use further hybrid models optimizations, and we can use diverse graphical data. We will also use a different type of renewable sources, and we will also use you can also use different methods to evaluate this model. So the limitation of our research study was high computational cost and high computation complexity, and it will basically extending the training data as much as the large data set as the real time forecasting is involved. So training time and load high computation is complex, and yes, very important fine tuning of hyperparameter, because this machine learning and deep learning is also this only focus on the hyperparameter tuning. So it's very important. It's have to be very it's a very limitation of our process. So thank you from myself. And if you have any question, you can ask. Thank you very much.
You, if you someone has question, please turn on your mic, or you can post in a chat box.